so let's talk about concavity. So again, we're going to go back to sort of a physical description of things. So let's talk about, let's say we have some function, maybe it looks something like this. This is y is equal to p of t. And what's happening here? Well, we have that the derivative of p, the derivative of position, is velocity. And further, the second derivative of p, which is the derivative of velocity, is acceleration. So what's happening on this region of the graph here? Well, if you were to graph the velocity, we see that it starts negative, then it goes up to 0, and it goes more and more positive, and the velocity starts to increase. So what ends up being true here? From this point onward, since the velocity is increasing, that's going to have to mean that the acceleration is positive, because for the velocity to be increasing, its derivative would have to be positive, like we talked about before. So this is a region on the graph where the acceleration has to be positive, and similarly, we can sort of see the function sort of slowing down here. This is a region where the velocity, the acceleration would be negative. So the function, it's decelerating here and accelerating here. But what else is true? Another thing that's true is that we can see that this function sort of looks like it's kind of has this upward scoop shape on this region here, and sort of has a downward scoop shape on this region here. So this is called concavity, and what we have is we have the following. So let's just give this as a definition. There are other definitions of concavity, and I'll just speak them out, but just as a definition, so we say f at x is concave up on an open interval if the second derivative is positive on that interval, and similarly concave down if it's negative. Now, just to speak out the second definition of concavity, which you might see at some point, another thing that you can tell from a picture to see if something is concave up or concave down is, let's draw a secant line here from this point to this point here. Concave up is going to mean that if you draw a line like this, your function is going to lie entirely below this line, whereas concave down means if you draw a secant line like this, your function is going to lie entirely above this line. So that's sort of two sort of graphical, more geometric interpretations of what it means to be concave up and down, but as it turns out, you can study this by looking at second derivatives. So that's what concavity means. And finally, just a quick definition. We say C is an inflection point of f if the concavity of f changes on either side of C. So, note, this means that f prime, the second derivative of C, is going to have to be 0 in this case, but you can have the second derivative at a point b0 without having an inflection point. So that's another thing that can go on. We'll do an example of that in a second. And note, for this function here, we see that this point here, C, is most assuredly an inflection point because the function is concave down up to this point, and then is concave up henceforth. Now, why do we care about concavity? Well, there are some other reasons to care about it beyond what I'm about to say. This gives us some interpretation of how acceleration is related to the function in the first place, and this is going to come up again when we talk about the second derivative test for finding extrema. But also, another thing that one cares about is being able to sketch out functions well. And of course, if you want to have a decent sketch of a function, it's pretty important to make sure that you clearly indicate where a function is concave up or concave down. Makes for a much nicer picture of a function if you get the concavity correct. So we're going to talk more about graphing later, and this idea of concavity is crucial to being able to graph functions effectively. So let's do some examples. So let's start out with a little non-example. If we have f at x is equal to x to the fourth, well, what does this guy look like? It's not quite a parabola. It's maybe a little sort of wider like this. But it looks about like this, and I think we can agree that this guy looks concave up for its entire lifespan. It's just a concave up function that looks very similar to the graph of f at x is equal to x squared. Note that if you take the second derivative of x, that's going to be, the second derivative of f, that's going to be 12x squared. So note that we have f prime prime of 0 is going to be equal to 0. I think we can agree that this doesn't look like an inflection point, but the second derivative of that point is 0. So this is why we have to be careful. An inflection point is a point at which the concavity changes. Any point where the concavity changes, assuming the second derivative exists, is going to be such that the second derivative has to vanish at an inflection point, but just because the second derivative is 0 doesn't mean you have an inflection point for sure. So keep that in mind. But now for some basic examples, in fact, similar examples to what we talked about before. If we have f at x is equal to e to the x, well, drawing this guy out, not only is he increasing, I think he looks pretty concave up myself, but indeed, if we take the second derivative of e to the x, it's again just e to the x, which is always positive. So yep, the second derivative here is always positive, so we're going to get a concave up function. E to the x is, if you will, constantly accelerating. Now, similar example again, 1 over x on 0 up to infinity. Well, if we draw this out, I would say that this looks concave up to me. It's, we have this sort of curvy shape. It's like a scoop up as opposed to a scoop down. It never quite ends up going up again, but nonetheless, this is definitely an up scoop as opposed to a down scoop. So we expect that this function is going to be concave up just from the picture, and it's going to be. And again, if we take the first derivative, we get this. And note now, just by the power rule, if we take the second derivative, it's going to be negative 2 all over x cubed, which is, of course, just 2 over x cubed, which, since we're just going from 0 to infinity, is indeed going to be positive. So yes, this function is going to be concave up. All right, let's return to this example. F at x is equal to x cubed minus 9x. We know a fair amount about this example, so let's just draw it out. We know that, at minus 3 and 3, it's going to hit 0, so it looks like this. And we know that these local extrema occur at root 3 and minus root 3. So indeed, for this example, well, I've drawn it a couple of times and I know how to draw it, but this is how you can know how to draw it, because anytime I've drawn it pretty clearly so that this part over here, we now see, because we now have the language for it, is concave down, and this part over here is concave up. And I think that's pretty obvious from how I'm drawing it, and if you get a computer to draw it for you, it'll be obvious from that picture as well. But Of course, the point of this is we don't want to have a picture first. We want to be able to figure this out just from the equations. And we can, because what's happening here, if we take f prime at x, we get that that's going to be 3x squared minus 9, so that f prime prime at x, the second derivative, is just going to be 6x, and we see that this is going to be positive, and therefore concave up for x is greater than 0, and this is going to be negative, and therefore concave down for x is less than 0. Which is exactly what the picture shows us, but note that it's not too hard for this function at least to figure this out just from computing the second derivative. And now, we do have that the second derivative at 0 is 0, but in this case this is an inflection point because it's a point where the function changes from being concave down to concave up. So we do indeed have an inflection point at x is equal to 0. So indeed, this is something that we can compute directly, and if you didn't know what the graph of this function looked like, you could then use this information to draw the graph and make sure that it scoops kind of down when you draw it on this region, and it scoops up when you draw it on this region.